The area of a circle is pi times the square of its radius. If we stretch the circle, we can make an ellipse. We can assume that the area of an ellipse is pi times the semi-major times the semi-minor. But why? Let's start by examining why the area of a circle is pi times the square of its radius. We will select a method for finding the area of a circle that will also work for an ellipse. We've chosen an approach that will have us draw overlapping rectangles to fill the circle. We will then find the total area of those rectangles, making sure not to double count any part of the circle covered by two rectangles, shown in green. We can then confirm that this total area is close to the area of a circle. If we want to be more certain that this approach is able to accurately estimate the area of a circle, we can fill the circle with more rectangles and calculate the covered area. Applying the same method for an ellipse, we can draw overlapping rectangles to fill the ellipse. We will then find the total area of those rectangles, again making sure not to double count any region covered by two rectangles shown in green, and confirm that this total area matches the formula for the area of an ellipse. As with the circle, we can better estimate the area of an ellipse by filling the ellipse with more rectangles and calculating the covered area. Let's start applying this approach to a circle. We'll place a rectangle on that circle, making sure its corners intersect the circle's circumference. We can then find the area of the rectangle. Knowing that the area of a rectangle is its width times its height, we need to find both the width and the height of the rectangle relative to the circle. If the width is some proportion a of the diameter of the circle, then in other words, the width of the rectangle is a times the diameter of the circle. We can find the height of the rectangle by placing a right-angled triangle in the circle. The circle's diameter is the triangle's hypotenuse, and the sides of the triangle are the height and the width of the rectangle. We can then apply the Pythagorean theorem to solve for the height. We now have what we need to find the area of the first rectangle with respect to the circle. The width is a times the diameter, and the height is the diameter times the square root of 1 minus a squared. The formula for the areas of the first and second rectangles differ only in the value of a, but we still need to find the double counted area, the region covered by the first and second rectangles. As the rectangles are shrinking in width and growing in height, the overlap has the height of the first rectangle and the width of the second rectangle. We can then substitute the formulas we recently found to yield an equation in terms of a of the first rectangle, a of the second rectangle, and the diameter of the circle. From that, we have that the area of overlap is a of the second rectangle times the diameter squared times the square root of 1 minus a of the first rectangle squared. We now have what we need to find the area covered by the first two rectangles, and that is the area of rectangle 1 plus the area of rectangle 2 minus their overlap. We can then find the area covered by the first three rectangles, which will be the area of the rectangles 1 and 2, plus the area of the third rectangle minus the overlap of the second and third rectangle. we can see a pattern emerging, which can be used to find a general equation for the area of rectangles that fill the circle. If there are many rectangles, the width of the last rectangle should be very small, so an will be roughly equal to 0, and the equation simplifies. If the radius of the circle is 1 and we fill the circle with 3 boxes such that A1 is equal to 0.75, A2 is equal to 0.5, and A3 is equal to 0.25, then the covered area is 2.49. If the radius of the circle is 1 and we fill the circle with 9 boxes such that A1 is equal to 0.9, A2 is equal to 0.8, and so on, then the covered area is 2.9. If the radius of the circle is 1 and we fill the circle with 9,999 boxes in a similar manner, then the covered area is 3.14. If we continue in this vein, we should expect that the covered area will continue to approach pi. We can again confirm this by converting the general equation above to an integral and solving. And we can see that the covered area is pi. We can now apply the same approach for an ellipse. We will fill the ellipse with rectangles and calculate the region covered by those rectangles. Once again, the first step is to calculate the area of an inscribed rectangle relative to the ellipse. In order to find the area of a rectangle inscribed in an ellipse, we need the equation for the points on the ellipse. We know that the equation for an ellipse centered at the origin is h squared equals px squared plus qy squared. We can put this in terms of major and minor axes by solving for p and q. And then replacing the p and q terms by the definition of A, we know that x 1 and 2 are equal to plus or minus a times the semi-minor. Using the equation for the ellipse, we can solve for y1 and y2. Knowing the values of the x and y coordinates, we can find the area of a rectangle inscribed in the ellipse. The area of overlap is again made up of the width of the second rectangle and the height of the first rectangle. We can use the equations to find the area covered by the first two rectangles, and that is the area of rectangle 1 plus the area of rectangle 2 minus their overlap. We now have an equation for the area covered by the first two rectangles. The area covered by an ellipse filled with rectangles can then be generalized and then simplified if we assume the last rectangle has an a value of 0. Given that the area of an ellipse is pi times the semi-major times the semi-minor, if the semi-major of the ellipse is 1 and the semi-minor of the ellipse is 0.5, we should expect that the covered area approaches pi over 2. If we fill the ellipse with 3 boxes, then the covered area is 1.24. If we fill the ellipse with 9 boxes, then the covered area is 1.45. If we fill the ellipse with 9,999 boxes, then the covered area is 1.57. If we continue this trend, we should expect that the covered area will continue to approach pi over 2. We can again confirm this by converting the general equation above to an integral and solving. Are you any more convinced that the area of an ellipse is pi times the semi-major times the semi-minor? Leave your thoughts in the comments. Thanks for watching.